Okay, so we're going to look at problems 3 through 6 in this video from the College Board AP exam here. So let me find my questions. So we'll start with number 3 up here. All right, so here we're asked to find, looks like the antiderivative of secant x tangent x. And here you just want to know your antiderivatives. Okay, namely, you want to know your trig derivatives here, because a lot of times people think it's okay just to memorize that the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared. But this question evidences the fact that, yeah, they look for the other trig functions too. If you know your trig derivative as well, you'll know that the antiderivative of secant x tangent x, which this symbol's the antiderivative or indefinite integral, if you want to call it that, would be secant x plus some constant. That is, the derivative of secant is secant tangent. So you need two things here. You need to know your trig derivatives, namely that the derivative of secant is secant tangent, and you also need to know that this symbol means antiderivative. All right, so knowing those two things, the answer is A for number 3. Looking down at number 4, okay, so this one we have, again, do we know our derivatives is what this amounts to. Let me write this down. Okay, so we have a given function, f of x equals 7x minus 3 plus the natural log of x. What we want to know is what's f prime of 1. Well, before you worry about f prime of 1, don't worry about the 1 yet. Just find the derivative, which if you know your derivatives, this one's pretty simple. The derivative of 7x is just 7. The derivative of any constant, negative 3 here would be 0. And we need to know that the derivative of the natural log is 1 over x. Okay, important that we know that. So this is a new function, the derivative, and now we want to evaluate this new function at the value 1. Okay, so here it looks like it's going to be 8. Right, so the correct answer is going to be E for that one. Now, what this literally means is that if you were to graph f of x, you were to graph this function and look at where the x coordinate is 1, the slope of the tangent line at that point is 8. Okay, so that's what we can interpret f prime of 1 to be. Let's do 5 and 6. All right, 5 is about limits. Okay, for a limit to exist, usually that means that it has the same limit on both sides. So for this one, it says which statement is false. You need to consider every answer choice. This is not one you can just do and then look at the answer choices. So A says the limit as x approaches 2 of f of x exists. That's true, okay, because as you come from the left, your limit as x approaches 2, where my arrow is going to be y value 2. It's not actually, it doesn't matter that we have a removable discontinuity here. F of 2 is 1, sure, but the limit doesn't care about that dot removed. Just what are you getting close to as x approaches 2? Well, you're getting close to y value 2. Similarly, on the right-hand side, you're getting close to that same y value of 2. So this limit certainly exists. B is almost the same question or the same scenario. The only difference is you don't have a removable discontinuity. So this, if anything, more obviously exists. The limit as x approaches 3 is going to be 5, both from the left and from the right. Remember, the answer to a limit problem is a y value. You are approaching the y or the f of x value of 5 here on both sides of x equals 3. So that certainly exists. Okay, C is definitely going to be the answer here. And this one's pretty straightforward if you know your limits. As you approach 4 from the left, it's going to approach y value 1.9, 1.8, something like that. Again, the fact that it's an open circle we don't really care about for the limit. It can't be closed on both ends or it wouldn't even be a function. But as you approach 4, x equals 4 from the right-hand side, you're approaching y value 4. So your left-hand limit is 1.9 or 1.8. The right-hand limit is 4. Those don't match. Therefore, it doesn't exist. C is correct. You probably want to consider your other two options. Ask, what about the limit as x approaches 5? Well, nothing wrong here. This is continuous, differentiable. Everything looks good. You're approaching 6 on both sides of x equals 5. Finally, E, what does it say? The function is continuous at x equals 3. Yeah. Okay. Continuous means informally that you can draw it without picking up your pencil. So yeah, we're definitely continuous on both sides. Now we're not differentiable because there's a sharp corner. Remember, sharp corners or discontinuities or vertical tangent lines would make it non-differentiable or undifferentiable, but that's not what's asking. It is continuous. Sharp corners are still continuous. You can draw that without picking up your pencil. So everything there is true except for C, which is correct. Number 6. Okay, so a particle moving along the x-axis, total distance. Okay, total distance. Now, total distance can be difficult based on how that function does. So let's see if it stays above the x-axis or not. So we've got 6t. So let's think about this for a minute. 6t minus t squared. Okay, so let's go to the board here. What we want to know is the total distance from t equals 0 to t equals 3. Now, there's a difference between total distance and total displacement. Total displacement is how far did you move from point A to point B over a given set of time. You can move 100 feet, but your displacement could be 0 if you started and stopped in the same place. Total distance doesn't care which direction you went or where you end up. It just cares on how far you actually traveled as you went. For total distance, you're going to need absolute values here. Okay, but absolute values aren't going to matter if the function is positive throughout our interval. So I'm going to write this down just to start with. And this can be a little confusing with the absolute value. Total displacement would not need the absolute value. And just to sketch out why that is, okay, let's say you have a function that does like this. Okay, and that's your velocity function. Okay, when you take the definite interval, it's going to take this space under the curve. It's going to add that as positive space. That's you're moving to the right in particle motion. And it's going to take this negative space right here. So I've got a different color. I do somewhere, but this is going to be negative space. And this is, you're moving right for a while, then you're moving left. And a lot of times they can cancel each other out. Say, for example, if these areas were the same, then your displacement will be 0. And your derivative, your antiderivative would end up being 0 here, or your definite integral. To do total distance in this situation, we want to take this value and we want to take the absolute value. That is, flip it up above the x-axis so that we can accumulate that as distance traveled, because we don't really care which direction we went. I don't know if that's made much sense to you, but long story short, if it's total distance, you need absolute value bars. If it's total displacement, you do not. Now, if you look at the function t squared minus 6t, we're going from 0 to 3. Okay, we can ignore these absolute value bars if everything is above the x-axis. Right? So just doing a quick inspection of that function, if I factor out a t, okay, the zeros of this function would be 0 and 6. Okay, so it's not going to change. It's either going to be all positive or all negative in that interval. So that's good. It doesn't change in the middle of 0 to 3. If you take just some representative, say 5, and plug it in here, 6 times 5 is 30. 30 minus 5 squared is going to be 5. That's a positive number. So this particular function is positive the whole time. It specifically, I don't want to ramble too much, but this function actually looks like this from 0 to 6. And we're only interested between 0 and 3. Okay, so somewhere in here. We're only interested in this part. So absolute value is not necessary because it never goes below the x-axis. So I'm going to remove this. That is, total distance and total displacement here is one and the same. So let's take the antiderivative.